Hello everyone, welcome back to another video for the series I'm Help You, and today I brought an algebra problem, and more specifically it's about polynomials. And the reason why I brought this problem is because I think it's been a while since I didn't make a video related to roots of unity, so I just thought it would be a great review about the roots of unity. And personally, I don't really like complex numbers, especially when they're involved with algebra, because it's more related to algebraic number theory. But I kind of gave up on number theory for this exam, at least for this exam. So I'm going to study more after this exam. So yeah, so that's why I wrote this problem, and I hope you enjoy it. Then, without further ado, let's start solving this problem. If P, Q, R, S are all polynomials such that this is true. Prove that x minus 1 is a factor of P of x. We know that this is the same statement as P of 1, or P of 1 equals 0. They're same, they're, yes. And it's quite obvious that we should use the roots of unity filter. So let omega sub 1, omega sub 2, omega sub 3, omega sub 4, omega sub 5 be the fifth roots of unity, where without loss of generality, omega sub 5 equals 1. Yes. Maybe I will rewrite them because I don't like it. Yes. And after that, then we could start substituting. Let's substitute omega sub 1. Omega sub 1 to the power of 5 equals 1 by definition, or by construction, plus omega sub 1 q of 1 plus omega sub 1 squared equals, and this is the sum of all the roots of x to the power of 5 equals 1, and by Vieta's formula, it's equal to 0. And we could do the same for the others. Equals 0 plus omega sub 3 plus omega 3 or equals 0. P of 1 plus 5 Q of 1 plus R sub 1 equals 0. Now notice that P of 1, Q of 1, and R of 1 are not constant. And no, they are actually, so what I mean by they're not constant is that they keep changing. And the reason why they keep changing is because the problem did not explicitly define the values of P of 1, Q of 1, and R of 1. Moreover, we don't have the explicit definition of P, Q, R, and S. Therefore, we could assume as variables. If we do that, then there's something interesting that we could try, and I think that is graphing. So I actually don't know how to graph 3D figures involving complex numbers. So x, y, z, p, q, r. So why don't we say this is p of 1, p, x, y, z, p, q, r. and this should be R of 1. But the thing is, when we usually graph in like polar coordinates, we have like real numbers here and image number here. But P of 1, Q of 1, and R of 1 could all be imaginary number. So I mean, they are all complex numbers. They could be, yes. So, can we still graph it? I'm not sure if we can still graph it. Because there's no way to represent real numbers and complex numbers in the same number line. Because if let's say this is like P of 1, then if you have like real numbers here, then we cannot place complex numbers here because we cannot compare the size. So yeah, we cannot do that actually. That means graphing is not a great idea because we actually can't graph it, I think. If you think we can graph it, please feel free to share it in the comment below. Anyways, let's scratch that and let's think of it like this. Equals R of 1 is a solution to the triple. And it's quite obvious because 0, 0, 0, yes. But how do we assure that this is the only solution? Is there any way to assure it? To assure that this is the only solution? Why don't we? Never mind. I think. Wait. Oh, almost there. Yes. Why don't we do this? So let's add all these. And the reason why we didn't do omega sub 5 is because substitute omega sub 5 here, then it's not equal to 0. Because that's a special case. Adding them, we have 4 times P of 1 plus omega sub 1 times Q sub 1, Q of 1 plus R of 1 equals 0. And what is this? This is negative 1. That's because plus omega sub 5 equals 0, but omega sub 5 is equal to 1, so it's negative 1. Therefore, 4 P of 1 equals Q of 1 plus R of 1. And let's substitute them like here. So we have Q of 1 times 1 over 4 plus omega sub 1 plus 1 over 4 plus omega sub 1 squared equals 0. And following the same fashion, we have plus omega sub 2 squared equals 0. Now, it's quite simple, I think, because we can actually start graphing for this one. What I mean by that is, without loss of generality, wait, well, are we allowed to do that? Yeah, assume that no, but so what I wanted to do here is let Q of 1 be like pure real number and R of 1 be like pure imaginary number. That way when we graph them, they both pass through 0, 0. So that's what I wanted to do. So that way we could assure that this is the only solution. However, I just realized that Q of 1, R of 1 could be complex numbers. I mean like something like 1 plus I or something like that. Now, are we allowed to say without loss of generality? No, because it's not symmetric. And also that doesn't really apply here. Then why don't we think of it like this? Yeah. Huh. Nice. Yes. Oh, great. So why don't we think of it like this? Just let's count the number of pairs of Q1, comma R of 1 here. And I believe it should be equal to 1 because okay. I think it should be 1 because we have two variables and they're linear. So these are all linear equations, and the if they were like real numbers, then we obviously know that they have one solution. But I think they also apply for the they actually do apply for the complex numbers too. So we can expand our real to complex because just think of it as solving the system of equation, like multiplying and then doing those stuffs. Then we know that we have one pair of Q of 1 and R of 1, which is 0, 0. So we just proved that this is the only solution, and that way we proved that P of 1 is equal to 0. I think I still need to study more about the roots of polynomials over complex numbers because I think that was the main problem that I faced while solving this problem. So I think the main kick for this problem is first noticing the fifth roots of the roots of unity. The second one is about the roots and complex numbers, so like complex roots of system of equations. So thank you so much for watching this video, and tomorrow I'll come back with another very fun and interesting problem. If you think I made a mistake or did not completely finish the problem, please feel free to leave it in the comment below. Thank you and see you tomorrow. Bye.